Hi, my name is Davood. I come from University of Cologne. Today, I would have a very short presentation as to convince you as to why we should learn these proof systems, or at least, be slightly interested in whatever people are doing in machine learnings related, again, to these proof systems. So about 6 months ago, very interesting news was published about AlphaZero, which is a model designed by DeepMind, which Google owns in, by the way, where it was able to get silver medal in an international Olympiad problems. That can actually worry us, physicists, mathematicians, logicians maybe, as to whether we might lose our jobs, especially the younger generation. So perhaps this alone should be motivating enough to learn these proof systems. But aside from that, let's see how they did it. I won't go into very small details, but I would be happy if you ask questions about how they did it. Just as an overview, so they started by taking some very general problems in some math books, 1 million of them, gave this informal, so this is informal in a sense that it is written in a human language, okay? So it is a math problem, already proved to be true, but it is in a human text. They took 1 million of such problems from different books. Then they fit these problems into some formalizer network, which was Gemini in this case, but it doesn't matter what model you put here because it just transforms the informal problems into formal problems. And what I mean by formal problems are the problems that are stated in a programming language. Here, for this case, Lean, which we are going to talk about. Once it's done, this is given to the solver network. This is where the magic happens, the AlphaZero, where these problems are solved by reinforcement learning. Now, before that, as you can notice, there is 1 million problems here, but it has become 100 million. And the reason is that in a reinforcement learning, unlike supervised learning, which I will explain what that is, we need a very huge data set so that the model actually understands what's going on. So in supervised learning, you have a bunch of data, labeled data. You have an input data, and you know what the target data should be. And you feed the input data to the model. Model predicts something, and its prediction is compared against the actual target with some loss function. It can be cross entropy, it can be MSE. It doesn't matter what that is. And once it's done, we take the gradient of that loss function and backpropagate with a chain rule. That's what happens in a supervised learning. But in a reinforcement learning or in general unsupervised learning, we don't have labeled data. So we don't know what the target data is. In this case, the proof of this problem. Well, we do know the proof of the problems, but we don't give them to the model. We want the model to figure it out itself. So what they did was that they took 1 million problems. They stated these problems in different ways with this LLM. They made it much larger, 100 million. And they give it to the AlphaZero. And during the reinforcement learning, which I will explain slightly what that is, formal proofs are produced. However, we know that these LLMs they tend to produce fake results confidently. You can ask ChatGPT some math problems and it might tell you some nonsense and it might actually emphasize on its nonsense. So how do we know that the proofs written by these LLMs are actually true? And that's what makes Lean and other proof systems special, because they can check the proof produced by these LLMs are actually true or not. So that's the point of making an informal problem a formal problem. But what reinforcement learning is, just shortly, Imagine a game of chess. If you just do a random pawn move, you cannot really tell whether in the course of the game, I mean in the next 10 moves, in 20 moves or something, whether that moves was actually good or not. And we cannot brute force it because the number of states is huge. So what we can do is to define some advantage function, something that tells whether we are in a good position or not. For example, if I move my queen somewhere that is going to be attacked by a lot of enemies, it is not a good estate. But if I move it somewhere safe, then it is a good estate. Good in a sense of chess. Here, we are talking about proofs, about mathematical problems. And a good state that we want to be in is a state that the proof becomes, so we like to have simpler problems. That's what I'm trying to say. So we start from a very complex problems. We want to make it simpler and simpler and simpler. So at each step, when these LLMs produce some proof for the problem, the goal becomes simpler and simpler in some sense. And this can be used to define some loss function again. So we reward the system when it can simplify the problem. With this, the model can be trained to converge to some weight that can predict the result properly. So this is a loop where the model produces some result. It is checked by lean whether the goal is achieved or not. If it was, then we are done. The model is rewarded. If it has not done the proof yet, the goal is checked whether the problem has become actually simpler or not. So that's the rough idea. I started my talk with the younger generation especially might be worried about whether these LLMs can take our job, especially in abstract fields like physics, math, and so on. There is a good side to it as well. So it's not just negative thing that these LLMs came to the existence, and that's namely making our life easier. We can think of them as some tools that we can use to at least solve the simple problems that we don't like to do with our hands. They can just prove some part of the very long proof that we are trying to prove automatically, and it is guaranteed by lean that the proof is actually true, so it's not a simple hallucination. You can literally consider it to be the math truth, make our life easier. So here, as you can see, I put two pictures, a shovel and a shovel crane. And what I am trying to say in this picture is that, well, people used to use just shovels. But as technology progressed, we made some machines and we do the same thing, but much faster, much more efficient and so on. Maybe there is a good reason to learn how to use this shovel crane instead of, just do everything by our hand. So that's for me.
Then I will now, let me zoom out even more, because normally when you give a talk at a conference, you have a result, and then you present your result, no? And so we don't have any results. But then the other reason why you could give a talk at a conference is that you are some domain expert, and you can bring your specialized knowledge to lay people. But we are not domain experts either, right? What happened is that the analysis that Davood alluded to was that in a few years your skills will no longer be needed. Sorry, the AI will take over and will fire you all like Elon Musk is firing our American colleagues. Sorry if that isn't funny to everybody, but we have to defend the Canadians in the room here, no? And then my plan is that when the AI fires you all, I will be employed for 1 more year because I can operate the pedantic back end that the AI still needs until a year later the AI also finds it out and fires me too. But okay, at least this. All right, and so with this, with this, we thought, okay, we should really learn this backend. We should learn how to operate this excavator. And so the question was, what is a good problem to get started? And so we thought, okay, maybe we can formalize quantum physics, but then a million people are doing that at the same time. So we thought, okay, why not we need a theory that's mathematically well characterized, that has a community that follows it, but maybe not too big a community so that we can give a thesis on this. And then we settled on Martin's review of general probabilistic theories as some interesting object that needs to be formalized. And so Davood started a few months ago doing this, and then we told Robert about it, and he was like, why don't you present what you have done? And so that's what I'm doing here. Or that's what we're doing here. And so that was the introduction. I will now tell you what I've learned in the past few months about the logic of these theorem provers. What can they do? What can't they do? And again, I'm not an expert at all, but maybe my advantage is that the things that confuse me are also the things that would confuse you. So I can explain them to you where a logician would just say, oh, that's obvious. And then when I'm done, Davood will actually show you like a few things he's already done, translating Martin to formal language and what happens there. Okay, good. So proof. So before we go to a formalized proof, we have to actually agree on what a mathematical proof is. And it turns out that when you sit down and learn it, that there is not actually agreement in the philosophy of mathematics of what that should be. It's a little bit like quantum mechanics. If a mathematician says, oh, I want to learn quantum mechanics, maybe first I should learn, the interpretation so that I know what these people are talking about. And then you realize that people don't agree at all. It's just that, the disagreement has been pushed away from the day-to-day work. So you can actually do physics without agreeing on the foundations, and you can do math without agreeing on the foundations. But if you want to formalize it, you have to at least think about it. Okay? And so there's two main traditions that if there's a logician in the room, apologies, I will completely slaughter your field now. So there's these two big traditions, classical and constructivist, and I will tell you a little bit about, how they differ. And then I will talk to you about type theory. And if you think that's super bizarre because type theory, well, that's what I thought. Okay, if you go like, sure, obviously, then you're smarter than me. Okay, so what's the proof? Okay, so a proof, I think we can agree, is a sequence of deductions. So what do we have? At any point in time, there is like a list of mathematical statements that we have accepted as part of the mathematical canon. And then what we want to do is we want to find deductive rules, so moves that allow us to deduce new truths from the old ones so that we can add it to the list of things that are now known to be true. So it will be an ever increasing recursive process. So what are deductive steps, moves that are legal? There's a few things that I'm pretty sure you've heard. I've heard it in my math education in the first week and then never again. For example, there is the modus ponens, which says the following thing. It's going to be incredibly obvious, but let me anyway spell it out. So if among the list of truths that has already been established, there is a proposition P, and there is a second proposition that says P implies Q, then you're allowed to conclude Q. Ha! All right, okay. Don't get too cocky because pretty soon we're going to get to obvious things that are not actually accepted. Yeah? And this little symbol here is called a turnstile apparently in mathematical logic. And it means you can conclude. Okay? Here is another one. This will play a role in a second. It's the conjunction introduction is equally bloody obvious. If among the list of things that you know to be true, there is a proposition P and Q, you might then deduce that P and Q is also true. Hooray. Okay. Good. Now you can say, all right, okay, so now we can ask, so which kind of deductions in general are legal? Now we have seen two, and this turned out to historically, this has given rise to big fights in the earliest 20th century, and they're very fun to read about. Can anybody identify these old dead men? These are, no, not here. Oh, you can. No, it's not Hilbert. Well, he also, he was part of the fun a bit later. All right, this is Kronecker. Here is Kronecker, and this is Cantor. And they had a big fight, yeah, because Cantor was inventing quantum-finite set theory, and he was really pushing the math machinery at the time to its limit. And there's people like Kronecker who were not accepting the output of Cantor and saying this is not mathematics. In fact, he called it religion for reasons I will show you in a second. And there were personal fights. For example, he was a professor in Magdeburg and really wanted to become a professor in Berlin because, well, that's obvious. And he was a professor in Berlin and was blocking him from becoming a professor in Berlin. And he died in a mental institution. So, but in the end, today, his type of thought kind of won, but with the provers, his kind of thoughts coming back. Okay, so that's sorry. So now so now let me tell you a bit what this fight was about. So let's first adopt a Platonic model of mathematical truth. And the Platonic model of mathematical truth, which is absolutely not accepted in the foundations of mathematics, but let's anyway do it today, is that every mathematical statement, every well-formed formula, which you will recognize as such, has an intrinsic truth value. Yeah, so every statement is true or not. Okay, so apparently in the earliest 20th century, the fight was about whether this is okay or not to do. Today, my feeling as an outsider is that it is accepted that it's okay to assume this. Okay, there's still some complications arising from it. Let me explain this. So first, in classical logic, yeah, this is what Cantor advocated. Any deduction, any way of producing a new truth from existing truth is legal if it's truth preserving. So the only thing you ask is, if all your assumptions were true, then the deduced statement also needs to be true. And you can say like, yeah, obviously that's a task of math, so what can possibly go wrong? That's what you should be doing. No, that's, Except for this way of thinking may give rise to non-constructive existence claims. Yeah, they are non-constructive proofs, you all know this, and in the early 20th century, people disputed some, like Kronecker, that they were meaningful. Yeah, so that's what he called religion. So where do these non-constructive existence claims come from? Of course, you can do something stupid and make a non-constructive axiom, like the axiom of choice or something. I mean, obviously, if you're called Kronecker, don't do that. But there's more subtle things, because logic itself can give rise to non-constructive reasoning and non-constructive existence claims. And one source is called the law of the excluded middle. And so, yeah, I was warning you not to get too overconfident, because now I'm going to say something obvious that will lead you to trouble. So the law of the excluded middle, or the lem, as we logicians say for short, is that for any statement P, we may deduce that P or not P is a valid truth, because that's truth value preserving in a Platonic world. However, this may give rise to existence proofs where you have no idea how to construct a witness of the thing that you claim to exist. For example, here's a thing. Do I have time? I will briefly show you about this. Here's a statement. The statement is there exist irrational numbers a and b such that a to the b is rational. Okay, that's a mathematical statement. It's true or false. Let me convince you that this is true. And here's a very easy proof. Okay, and it makes a distinction. So it says either square root of 2 to the square root of 2 is rational, or it is not rational. That's a true move according to the lem. Okay, so if 2 to the square root of 2 is rational, well then we are done, because square root of 2 by Pythagoras famously is irrational. And we just assumed that 2 to the square root of 2 is rational, so we found an example. Or maybe it is not rational. I mean, who knows? Well, if it's irrational, then take a to be 2 to the square root of 2, and b, which is now irrational, which we just assumed, and b equal to square root of 2, which is irrational by Pythagoras, then a to the b is 2 to the square root of 2 times square root of 2, which is 2 square root of 2 squared, which is 2, which is rational. Okay, so now in either case, there exists such a pair AB, but unless you're pretty good at number theory, you have no idea, you cannot produce now a pair AB that has this property. Huh? Okay, so Kronecker would say that is not math, that is religion, and he would reject this as a valid argument. So now I've portrayed these people like Kronecker as kind of like negative people who reject proofs, but they also did something constructive. And they came up with a way of doing mathematical deduction that is not only truth preserving, but also preserves constructibility. Yeah, so if we'll make it precise in 5 minutes, but now slightly imprecisely. So if all your existing truths, like P1 to Pk in my beginning, they are all true and constructible, I want to now add new truths that are both true and constructible. Yeah? And here are their interpretation of Brouwer, Heiting, and Kolmogorov of how to do logic in a constructivist way. And you will see this, the spoiler now, that this way of thinking that was designed in the early 20th century is extremely computational in flavor. And it's a very good match if you want to reason on a machine. And so the machine reasoners, like Lean, for example, the system I want to present, they all work in this kind of philosophy. So it's a good idea to think about it a little bit. Okay, let's start with the easy things. And so they say, okay, if you want to deduce a conjunction P and Q, you have to now supply a proof of P and a proof of Q. Okay, yeah, that's obvious enough. Let's go to disjunction, which is a bit more subtle. So to deduce a disjunction P or Q, you must supply a proof of P or a proof of Q. That is different from what the classical people assumed. No, it's a stronger requirement. I don't just say P or Q must be true. That's insufficient. I have to tell you which one it is. So the lem is no longer generally valid. Okay? And they go on, and this I like the most. I think like I learned this, and for one day I was telling random people on the hallway, sorry if some of you suffer. So to deduce an implication P implies Q, you must supply a procedure for turning a proof of Q into a proof of P. I think this is genuinely a different way of thinking, and it's generally a super good match, obviously, you know, for an operational or computationally thinking person. Yeah, and that's what an implication is. It gives it says any reason that P is true can be turned into a reason why Q is true. Q and P should be interchanged. Okay, another one which is also related is like to deduce a universal statement. So for all x, P of x is some statement depending on x. You must supply a procedure for turning x into a proof of P of x. Is that right now? Yeah, I think it's so. And so one thing that this also makes sense. So one thing that you see is that an implication, a proof of an implication and a proof of a for all statement are basically functions. Yeah, these are functions mapping P to proof of P to proof of Q. That's a function mapping x to a proof of P of x. And indeed in this Lean system, there is not actually a distinction between a for all quantifier and an implication and a function. That's all the same object. Yeah? So they use the same symbols. They take this very seriously. And so on and so on. There's more items to the list. For example, negations are kind of subtle, but I will skip over them. And again, what I said is a very computational flavor, so it's a good foundation for computer-based systems, and the computer-based systems all think in this constructivist way. And then something surprising happens, which is, I think, why you should be taught this by a dilettante like me and not by a logician, because they would just now assume that what I'm going to say now is obvious, where I think it's bonkers. And so the second ingredient, so first ingredient is constructivist logic, and the second ingredient is type theory. What is type theory? So if you're an old, now you can't see it because it's on a different screen. Ah, shit. Okay. So if you're an old person like me, you've learned maybe coding in C or something. And there you have learned about types. I'm making it bigger so you can see. Okay. So type theory, like to an old person like me, is that you put like int in front of your variables to tell the computer that's an integer and not a floating point number, so that it will interpret the bit patterns differently. Yeah, and then a compiler has some logic called a type checker. So if you write stupid stuff like int x equal to, and on the right hand side you write a floating point and you compile it as I did here, then the type checker issues you a warning that you're doing something stupid. Okay? And so that's what type theory used to be to a person like me. And so now apparently this is important in computer reasoning. I mean, I don't know. Okay, so let me try to tell you how the story goes on. So then let's briefly talk about universality. So you all know here, or most of you will know, that there are many systems that are universal as computers. Like maybe first I give you some serious examples, and the serious examples are Turing machines. They are universal for computation. Or gates on silicon chips, they are universal for computation. Or obviously local measurements on a cluster state. No, these are universal models of computation in a serious way. There's also unserious ways of universalities. People have like lots of fun doing this in the internet. There's like this web page, accidentally Turing complete, where people like collect random shit that is universal, like HTML5, it says HTML, HTML5 and CSS, Minecraft, PDF. So what does that mean? PDF, for example. PDF is a system for displaying things on a printed page, but it's Turing complete. So what you can do, in fact, is write Doom in a PDF. So that is a PDF that's being displayed here, no? And so it is apparently computational universe. Oh, you cannot see it again. So here, this is a PDF, and you can play Doom in a PDF. So if your firewall does not filter out PDFs, you can still play Doom on your office computer. All right, okay. So let me close this because it will kill my battery life. Okay, so now there are also many systems that are universal for logic in a serious way. For example, Hilbert, who wasn't on my pictures before but also played a role here, he came up with the Hilbert calculus for logic. Other people invented the Tableau method for logic. And then somebody realized in classical logic that type theory is universal for logic. And then there is like us on one corner and the theoretical logicians on the other corner. That's Martin Löf is one of the big people there. And when I hear that type theory is universal for logic, I go like, yeah, you run Doom in your PDFs too, huh? And then, because Martin Löf apparently is a young person on the internet, he says this, but unironically. So it is actually true that these logic systems are built on constructive math realized in a type system. It's bonkers, I tell you, but this is how it is. Okay, and so of course, why it's not completely unreasonable is that types are much more complex these days than just int and float. For example, you can now, like, I don't know, here's my C++ example. Davood had an example in Python the other day, but I'm old enough, I can only use C++, where you can define your own custom data types. Like, for example, you can define a data type for complex numbers, and then to instantiate it, you call a constructor, and the constructor takes two numbers, x and y, a real and imaginary part, and then outputs a complex number, right? And so they are much more, this is constructions and complex types, they are much more difficult these days. And okay, and so in Lean it is true that every mathematical statement defines a type, namely the type of its proofs. And all the system does is to reason about types. In fact, this will also confuse the hell out of you if you try to learn it for the first few weeks. It identifies statements with this type. So a mathematical statement in the computer system is identified with the type of its proofs. So it means that to prove a statement, you have to construct an object of this type. Okay, so that's what we'll be doing now. We will be constructing objects of such types. Okay. So now, okay, so what is Lean? It's a very big system. It is a Lean kernel that is Lean indeed. There's an IDE for constructing proofs. It looks like this. That's, you see classical cone, effect cone, blah, blah, blah. That's, what Davood has done, and he will show you in a minute. And then it comes with mathlib, which is many gigabytes of proven math. For example, it knows about SH and the Tyrrellson bound. It's already there in the library, many, many gigabytes. And now there are two learning strategies for learning the system. There is the top-down way, where you build on all this knowledge and you do some math that you recognize, and Davood will show you how this looks like in a minute. And there's a bottom-up way where you just play with the naked kernel to understand how this thing actually operates, which is what I will do now in the next 5 minutes. Okay. All right, so now it's the preparation before I switch to the console and show you how it works. Okay, first a preparation. So think about the following. Maybe many of you know MATLAB. No, it's a package for working with matrices. MATLAB knows about matrices. That's what it's good at. Microsoft Word knows about words. Excel excels at numbers, obviously. And so you would think that Lean is a tool for math proofs, so you should think it knows a lot about math. Let me list a few things that the kernel, so the base system on which everything builds, does not know about. It does not know about arithmetic. You can't say plus, it says plus what? It does not actually know about numbers. You can't say 1, it says what? It does not know about logical connectives and or not, never heard of that. It does not actually know what true or false means. It ain't called lean for nothing, yes, Martin. This guy, you know. All right. So what does it know? It has very few primitives and builds everything out of those. And let me just list 2 or 3 of them. So one is, there's a very small number of predefined types. For example, prop. Prop is a type of mathematical propositions. Every proposition will be of type prop. And now the confusion begins. I will tell you, but you will anyway be confused. I told you that every mathematical proposition is a type. It's a type of its proofs. Now I'm saying you it's of type prop. So the downside of the system was that it was built by logicians and they really like hierarchies. So what the system has is a type hierarchy where every proposition defines the type of its proofs but is itself an element, has itself a type, namely prop. So every object of type prop is itself a type, the type of proofs of said proposition. Okay? There's also another predefined type which is called type. It's a type of, look! It's the type of types representing concrete mathematical objects. It's called the data carrying type. I could talk about the difference in more detail, but I don't have time. Then there is inductive types. That's a powerful way to define custom types. It's like the class keyword in C or C++. Yeah? And so this is actually what we're going to use. And then there is a very general way of building functions. So we have a few types, a way of defining new types and talking about functions. That's it. It's more interesting that I can make a false type. The false type is much more subtle than the true type. Now, fine. So here's the system in action. Can you see it? Okay. All right. Later, I will import something from the standard library, but now I don't. So I use nothing but the naked kernel here. Okay. So first, let me define a data type, which later we will be identifying with the logical end. And so I will now, walk you briefly through these complicated set of declarations. So inductive means I'm declaring a new complex type. It's like the class keyword. And it's called end. That's just the name I made up. I could call it something else. Right, okay. And it takes 2 arguments, namely P and Q. And P and Q are here meant to be propositions. That's what this colon says. P is an object that is a proposition, and Q is an object that is a proposition. And giving these 2 ingredients, I can now construct an end. Okay. Okay. So it's okay. So the type depends on 2 propositions, P and Q. So you should really think about it as defining a family of types, namely end PQ, depending on this. Okay. So now the big question is, how can I? What is the constructor? How can I construct an object of type NPQ? And the constructors are listed here in the body. And there is only one constructor, and the constructor I called intro, it's just the name I gave it. And the intro, and now it gets the type hierarchy comes now back in, so you will be super confused in a second. It takes 2 arguments, one of type P and one of type Q. Okay, so let's think about this. P is of type proposition, so P is a proposition. HP is of type P. But every proposition defines the type of its proofs. So HP is a proof of P. So in order to call intro, I need a proof of P and a proof of Q. And if I give it a proof of P and a proof of Q, I get an object of type NPQ. That's what this definition says. So then what's happening here is that, let me just say it here, blah, 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 blah. It's not an overloading in the sense of computer languages, but it's an overloading in the sense of overloading our brain. That's what I said before. So these 2 concepts are identified in this community. And they have been identified in that community since about 1960, which is why if you read their papers, you are super confused because they don't think that's noteworthy or something. But yeah, that's what I try to, yeah, but you're totally right. These concepts are identified. Okay, so we call the constructivist conjunction introduction rule, where we said to prove P and Q, we need a proof of P and a proof of Q. And to construct an object of type NPQ, we need a proof of P and a proof of Q. So this data type behaves exactly like the end, the logical end does in constructivist logic. And now you have to go through a small process, which I will take your hands and drag you along, because that's what happened to me. You go like, yeah, But that's not the real logical end. It doesn't know any semantics. It doesn't talk about end. It's just a data type that behaves formally the same way as a logical end does. Oh, it behaves formally the same. Well, what do I expect? Yeah, that's what formal logic is all about. So we are just coming up with formal constructs that behave in a type sense in the same way as as these logical primitives would do. Yeah, and so now, so the built-in end, so the standard library has a built-in end, it's defined exactly like this. Yeah, just a data type. Okay. Right, now let me show you how to do a concrete type. I will now define another type. It's inductive. I call it NUT, because later I will argue that it behaves like the natural numbers. But again, just a name. It's not referring to any built-in primitive here. It has two constructors. One I call 0, just because I like the word, and the other one I called suk. And 0 just gives you a nut, but suk takes a nut and then gives you a nut. That's it. So these are the two constructors. So let's see how this behaves. Okay, so the only way to construct an object of type nut is to call the 0 constructor, because the other one already takes a nut as an argument, but we don't have any. So to put a nut in the world, we have to call nut 0. And then if I do it, the eval statement tells me what it evaluates to, and it evaluates to nut 0. I have now constructed a nut, an object of type nut, namely nut 0. Okay? Now that I have one, I can call the second constructor, and I can construct a nut suk nut 0. And what does it evaluate to? Nothing. Nut suk nut 0. It just holds its arguments. Okay, I can call nut suk again. It evaluates to nut suk nut 0. Okay, you can kind of see where this is going. It doesn't actually reduce anything. The constructor isn't doing anything. It just holds its arguments. But you know, this formally behaves just like the natural numbers. No, there is a 0. And for every natural number, you can turn it into its successor. And so every number, every concrete mathematical object indeed derives from that construction. Yeah, but it does not know more about the semantics than just this. I can define some shortcuts like def0, def1, def2, and now I can, eval 2, and it will evaluate to nut suk, nut 0. This is how internally natural numbers are represented. Okay, so now you can do, and now is the actual power, you can define functions on such inductive types. So I can define a function that I call plus because I like the sound of the word plus that pleases my ears. It has no semantic notion of what it means to put 2 pebbles into a box with 1 pebble and get 3 pebbles out. Yeah? And plus takes 2 arguments, k and l nuts. And what does it do? Well, if L is 0, it just returns K. But if L is a successor, it returns the successor of plus Km, a recursion. And then Lean understands that this is well defined. So it has some kind of induction axiom built in. So and now I can start doing arithmetic. I can call plus I can call plus of the successor of 0 and 0, and the evaluation is, so that is plus 1 and 1, and the evaluation is nut suk 0, so it actually tells me that it's 2. Okay. So now let's go back and let's create some propositions, because before we could combine proposition with an end, but we couldn't create a proposition. So we will now define what equality means. It's funny because it doesn't know what equality means, and again we just make a data type that formally behaves like equality. So we call it equal because just with foresight. And it takes 2 arguments, a and b, and it's supposed to be the proposition a is equal to b, which could be true or could be false. And it's true if I can construct an object of this type. And so I will define only one. This is super, like, equality is still blowing my mind. Yeah, we define only one constructor, which is called reflectivity in Lean. And if you give it, it takes 1 argument and produces an instance of equality with the 2 being the same. And this is just, again, a formal type theoretic construction, but it means the only way to get a proof of equal AB is if A is actually equal to B in a meta-theoretical sense. Does it make sense? That was not a joke. That's a normal logician lingo. Fine. So it's okay. So it's equal is just a data structure where the only way to instantiate an element of the data structure is if the 2 arguments are the same. So that's the only thing, you know, that's all about equality that it uses. Okay, and now I have to really hurry. Okay, now finally I want to tell you how to prove things. For example, I can now prove that 1 plus 1 equals 2, in fact. So, and now how do I prove this? Okay, first, what does it mean? So first I say, okay, theorem is a keyword that indicates my intention to now prove a theorem. Yeah, but that's it. So it says, okay, go on. There's a misconception yesterday I found during dinner. These are called proof assistants, but they're really proof opponents. So they don't, this is, before you shouldn't have laughed, now you can laugh. This I super mean. They don't help you to make a proof. If you have a proof in your head, you can try to teach that system, and if it's correct, it will accept it. But it will fight you all the steps on the way because it's super pedantic. So when I say theorem, it just says, okay, go on then. Now I give it a name, 1 plus 1, or I could call it Jens, it doesn't matter. And here's now the type. Colon always means we come to type. And the type is equal plus 1, 1, and 2. Okay? So now I have declared my intention to show that there exists an object of the type 1 plus 1 is 2. Now I have to construct an object of the type 1 plus 1 is 2. And it's fundamentally an object of type equality, which I can instantiate by calling a constructor of equality. The only constructor of equality I know is Raffle, and I give it the argument 2. It now constructs an object saying that 2 is equal to 2, and then Lean evaluates the recursive function, finds that it's 2, and accepts it. So now Lean knows that 1 plus 1 is 2, but not, of course, the numbers, just my data type. I just made up all these things. Okay. And so then we go on, we can do an end, but I will skip it. And there's some fun stuff here. Okay. But we started 5 minutes late and I'm 3 minutes before the end time. So if we have any chance of getting to see what it looks like on the high level, once you serve the 5 gigabytes of type assessment that come with MathLab, we should switch now. And so I switch now here and go back to, you want to have devs? No devs, or you want to have, which file do you want to have? Classical. All right. Okay, so now this is after some time. All right, formalizing GPTs. How does it actually look like if you don't, like me, work on the bare metal, but if you use all the abstractions that the system gives you?
Yeah, but just before that, I wanted to answer your question because I couldn't. I don't know how to integrate, especially in Lean. So I can give you a simpler example, namely proving that 2 plus 2 plus 2 is 6. And yeah, that's the best I can do. So let's say I have a function that takes 2 and gives me 2 plus 2. And if I compose this function with itself, it gives me 2 plus 2 plus 2, right? So this is a nested object that I was talking about. Now, to actually prove that 2 plus 2 plus 2 is 6, we can simplify this by one step, namely showing that f of 2, and this f is the function that I was talking about, is actually 4. So 2 plus 2 is 4. So my equations, instead of 2 plus 2 plus 2, becomes 4 plus 2 is 6. Okay. So it is simpler in a sense that I have deconstructed my nested object. Also, the number of terms in my equality has reduced from 2 plus 2 plus 2. It has become 4 plus 2. So that's precisely what I meant by making things simpler. And the model is rewarded with these simplifications. Now, yeah. So, yes, so something maybe, yeah, this orthron looks good. So we can define this by, well, a set of objects. Here, this V, you can think of it as a vector, that each of its components are positive. So take, for example, R2, so the normal 2D system. The positive part of that coordinate system is what we are interested in. And the set of all points in that system can be defined by this set. As it was said, in Lean, we first need to tell Lean what even we are talking about, and this carrier contains this set to basically tell the Lean that I am talking about the objects inside this set. Now, we want to prove that this entity is actually a closed convex cone. Okay, let's see what this closed convex cone means first. So, okay, a closed convex cone is a convex cone that is closed. And a convex cone, okay, is a cone that is convex. Yeah, I am stating obvious now, but so let's start from cone maybe, which is even a simpler object. A cone is an entity that is invariant under scaling. So take a bunch of vectors, scale them by some positive numbers, scale it arbitrary. The set you get from doing so would be a cone. That's what it is. And convex cone is just adding convexity to the cone. So if you add two vectors from this set with proper coefficient that are summed to 1, then you have a convex cone, and closed in a topological sense. So topology is the set of open sets and closed in that sense. So that's how we define these things, and now here we have proved that this orthont is actually a closed convex cone. So how? First, we tell it what an orthont is. Then we prove that under the scaling, so if I multiply the vectors inside this set by some positive number, whatever object that I end up with is actually inside this set, it doesn't go outside of it, is proven here. So this is high level stuff. Again, we use tactics. So this by is a keyword defining Lean, which tells Lean that, okay, I want to start to prove this statement. And it creates a goal. And the goal is, as you can see here, I don't know if it's clear or not, but the goal is, as I said, take some positive number, take some vector inside this set, and prove that if we scale that vector by some positive number, then it is inside the set. That's it, really. So now we want to prove it. And okay, so we first assume the assumption in our mode exponents. We assume we have some arbitrary positive number, which I call it C, and a proof that it is actually positive. Oh, that's what I wanted to show. And also a vector, a component of that vector. So this I refers to ith component of that vector here. And the proof that all of the components of this vector is positive, then I need to show that this scaling would retain the positiveness. So,
and see, it doesn't assist you, it just says, okay, now what's your next move? No?
Yes. So Lean actually have a simplifier, no LLM, nothing. It's just a deterministic algorithm that can simplify certain statements. For example, the sets are defined based on propositions in Lean. I don't have much time, I guess, to explain what that means, but it can simplify this statement, namely V belongs to a set of objects to this. So here it just says that all components of the vector are actually positive. So it deconstructs the set into the actual proposition that creates that set. That's all I am saying. I can simply prove that after multiplying that vector by a positive number, I remain positive by saying that, okay, given two positive numbers, if I multiply them together, I get a positive number again. And it is already proven by some other people. I'm just reusing their own theorem. So this thing that you see here is actually a theorem that is proven already. So we make our objects based on the things that people have done in MATLAB already. And same goes here. I won't go into details. It's just the same concept. We take two vectors, we take two numbers, and we have a proof that the sum of those numbers are 1, and then we need to show that the resulting vector is actually within the set. Again, this simplifier can simplify our life, make our life easier, but sometimes we need to give it some information. For example, here, doesn't show, yes. So here, this one might seem super obvious that if x is larger than y, I can say y is smaller than x. Obvious, right? But Lin doesn't know that. It needs a theorem that proves this, and you have to give it that theorem. Yeah, sometimes I spend hours to just find some simple arithmetic theorem, so that's a warning here. But and lastly, I think that would be enough for explanation of orthons. We prove that it is closed with respect to the topology. Now, which topology? To keep things as easy as possible, we took Euclidean vectors. So in a sense of Euclidean space, as easy as that, where the norm is defined by supremo. To prove that an orthont is closed, we can firstly say that an orthont is made by intersection of a smaller set. So if you think about it, where was the set? It was here. So there is a for all statement here that says for all components it's positive. But you can remove that for all and put an intersection between the sets that contain only one component of the vector, and they say that component is positive. So that's what it is basically. It says that if you provide me with a proof that for all components it is closed, here. This one, yeah, I am not used to this, but here. It says that if you provide me with some proof that all components preserve the closedness, I can give you a proof that the intersection of all those sets are actually closed. So we use this, and then we use another theorem provided by other people that says, given two continuous functions, I can give you a proof that this set is closed. Okay, so in my orthont, I have a 0. 0 is a constant function, so it is continuous, of course. And vi is just a projection, so you take a vector and project to one of its components. And it is also continuous. So I give it the proof that this is a continuous, so 0 is continuous function, and also the projection is continuous, and I'm done. Basically, I am proving that this orthont is a closed curve. Okay, but why should we care, right? So I think the idea is that we, after proving a lot of stuff, extending this library, we can let other people use it, and also LLMs can be trained on these libraries, and later, hopefully, make our life easier.